Screen is visible?
Yes, sir.
Yeah. So today we have a very interesting discussion and very important discussion. I hope everyone pay more attention to learn this because why it is more important. Again, I'll tell you the whole subject is all about. I can say some not a theoretical concept. I hope you can understand. Okay, we design some theoretical machine. It means it is all about the problematic one everywhere from this is our 11th class. I hope for all 11 classes I interacted everything with the problematic component only because I'm always writing something. I will not simply show some architecture and explaining that flow of the architecture or the procedure of the architecture or the functionality of the architecture. I'm executing everything with a problem and some writing component only. It means it is actually a problem based subject, full subject. You have to keep on writing something, not simply look at some image and you have to explore. No, you need a paper and pen along with you whenever if you are learning or reading the subject. Okay, so with that the very important conversion, again I'll tell you this is a whole subject all about a conversion. There are many conversions are there. Say for example, initially we have seen any general language, you have to define the corresponding machine. Yes, any given language, you have to generate a corresponding grammar. Yes, in that machine also, one type of machine you can convert it to other type of machine. Yes, even some languages also will be given in some other form. You have to create the machine for it. Yes, for that machine also you need to perform again conversion. Likewise, the whole subject is all about infer something, convert something. So this will be there for the complete syllabus. So you just recap what are all the conversions we have done as of now and what is the conversion which we are going to do for a today's class. Okay. So now for a today's class objective is, as I told you, whenever there is a language will be represented in the shorter notation is called as a regular expression. So I don't want to say that all the language will be represented in the regular expression. So right now we are in the first type of language. So whenever there is a regular language, that regular language will be represented in the shorter notation is called as a regular expression. So now the question is what you wanted to do. Generally, what you will do for this regular language, you have to design the machine. For regular expression is also a language only. Regular expression is also a regular language only. The shorter notation of regular language only, I'm using some expression. The name of the expression I can call it as a regular expression. So now with that regular expression also, what I supposed to do? Simply I'm going to design a machine only. So what is the type of machine which you are currently reading? The type of machine we are reading is the finite automata machine. In that finite automata machine, what are all the different types are there? There is something is called as a NFA and there is something is called as a DFA. Only these two are there. No, we have a two more type which I have discussed many times. That is a with output category, Merli and Mori machine. That is the last topic of this unit number 1. Now you can see with respect to NFA and DFA. Now what is the question? For the regular expression, you wanted to design either the DFA or NFA. Which one actually you want? You want only DFA only. That's why the topic is to design the DFA from the regular expression. But from the regular expression, you wanted to design the DFA. But somebody is talk something. Hello. Okay. From the regular expression, you wanted to design the DFA. Now the direct designing of DFA is possible? Definitely not. Then what is the other way? Only the workaround fashion. What is a workaround fashion? Regular expression to direct NFA you can do. Yes, definitely you can do NFA. From the NFA, you can able to design your DFA. Super. So what method you have to apply here? You have to apply the subset construction algorithm. Subset construction algorithm you can apply. So this is we have already discussed in the last 2 classes. Okay, the last class we have discussed. Okay, I will come to that. The other way, you have to convert the regular expression into epsilon NFA. From the epsilon NFA, you have to design your DFA. Ultimately, what is your goal? You want to design the DFA from the regular expression. Yes, of course, we can do in this way. Now the question is, even for epsilon NFA to DFA, we have to apply the subset construction algorithm only. Okay, so now what procedure to do the regular expression to NFA? Do we have any algorithm or procedure to do that? No, we don't have any algorithm or procedure to do that. We have to manually write our NFA with our knowledge. Whenever there is a loop, whenever there is a closure, what I am supposed to do? Whenever there is a union, what I am supposed to do? Whenever there is a concatenation, what I am supposed to do? With a general understanding only, I can do this NFA conversion. From that, I can do DFA. But if you want to do any patent or algorithm you want to follow from a regular expression to NFA, yes, we have one algorithm is called as Thomson construction algorithm. So with the Thomson construction algorithm, you can convert any regular expression to epsilon NFA. So, oh, please, who is that? The host, can you please mute everyone? Okay, so from a regular expression, using the Thomson construction algorithm, we can get the epsilon NFA. This is what we have discussed in the last class. So right now, what we have in our hand, we have a epsilon NFA in our hand. So how the epsilon NFA will look like, which we have practiced many examples in the last class. More than 10 examples, 10 regular expression I have taken. I shown you how you supposed to draw the epsilon NFA. Now from the epsilon NFA, you can able to convert the DFA. So by using what? A subset construction algorithm. Okay, so now the subset construction algorithm which you have used for NFA to DFA, the same procedure we have to follow here. A small difference in the procedure to convert any epsilon NFA to DFA. We have some small procedure. The procedure is nothing but epsilon closure, or we will call it as E closure. There is one computation is called as E closure. So that is a small feature which is added in the epsilon NFA to DFA conversion. But for NFA to DFA conversion, there is no such procedure. You can directly convert the DFA transition table, which I have discussed while I'm discussing the NFA to DFA conversion. Okay, so now what we are going to see for today's class, epsilon NFA to DFA, using what? Substitution construction algorithm. Along with that, we have added one more feature is called as E-closure feature. So by using the E-closure feature in the subset construction algorithm, we have to convert the epsilon NFA to DFA. That is what the discussion for today's class. Okay, sir, from this converting the regular expression to DFA alone, the overall transition is over? No. Still, we have one more procedure in this result. Whenever there is a DFA, you can get literally what DFA? DFA is a machine, consists of what? A collections of state. And there is one starting state, and there are many final state, and there is a transition. This is what the overall DFA. There is a chance you can able to reduce the number of states in the DFA and produce the minimized DFA also. Minimized DFA. But both the minimized DFA and the normal DFA will give the reflection of same language only. There is no difference. But whatever the result this DFA will give, the same result we can also able to give with the minimized DFA by reducing the number of states alone. So that's why the next transition is DFA to minimized DFA. The next transition is DFA to minimized DFA. Okay, so now again you may ask the question, okay sir, for a DFA to minimized DFA, again do we have any specific procedure or algorithm? Yes, we have one procedure is called as state equivalent procedure. State equivalent procedure. Okay, there is other method is called as table filling method. See, there is a method is called as a table filling method. There is a method is called as a state equivalence procedure or state equivalent method. So these two will help us to convert the DFA to minimized DFA. But you should not worry, the DFA to minimized DFA as per our syllabus which is available. See, who is that? Venkatesh, please mute everyone. Venkatesh, are you there? So the DFA, to minimize the DFA, you should not worry about now, because for this component we have it in our unit number 2 only. Okay, so that time I will explain more about the DFA to minimize the DFA using state equivalence method as well as the table filling method. Okay, now you no need to worry much about this. We have only transition between these two. See, if others also don't feel that the disturbance by someone else who is
ఇప్పుడే ఎందుకు అన్ని తర్వాత
yaar, Sai. Sai, who is that Sai only, no? Sai Dattu. Sai,
ఓకే సార్
unmute. Mute everyone. Please don't disturb. Okay, so you don't worry about this minimization. That could be discussed in the unit number 2, but it is also a part of this procedure. Okay, so now where I wanted to discuss, or where I wanted to take you, I wanted to take you to the epsilon NFA2 DFA conversion. Okay, so now I will zoom. Okay, so now tell me someone, what is this? Open parenthesis a plus b. What is this? What is the name of this? See, continuously the last class and followed by this class, I have another class also. I'm having that energy to discuss, and why you people don't have? What is this? A plus b. The a plus b is nothing but a regular expression, because you can see this is a union operation. The regular expression, we have only 3 operator. One is a union, concatenation, closure. So what is this? Literally, this is the regular expression. What I supposed to do for the regular expression? For the regular expression, first I have to design the epsilon NFA. Okay, so what is that epsilon NFA? How to do that? So this is the epsilon NFA. Whenever we have a union, then from a starting state, as per the Thomson construction algorithm procedure, I have one path will go to one direction, other path will come to other direction. So what is this information? Either I can put lambda or epsilon. Both will represent that empty string. So without with reading empty string, I will go to Q1. From Q1, by reading A, I will be here and I will reach final state. The other way is B. So as per this regular expression, what is this regular expression? It is representing one language, right? So as per that language, what are all the strings of the language? As per this expression, there are only 2 strings. One is A, another one is B. Only these 2 strings only will be accepted. Yes. Now, what way I can able to design the DFA for it? Okay, so we will see the result directly. See here, whenever there is a go to final state. Whenever there is a B, go to final state. Okay, whenever there is a from other state. Okay, so that I will explain you. Here there are some unreachable states are there. Finally, you will be come up with only 3 states. I will come to this result. Finally, if I am writing directly the DFA for this, I can write the DFA like from a Q naught simply. If you are reading a single A, there is a chance you can able to reach the final state Q1. Okay, and the same way, whenever if you are reading single B also, you will reach the final state. After reading final state, if you are reading any A or B, you will not be allowed to reach the final state. Okay, so it is a non-final state. I can say that Q2. And from the Q2, if you have any A or B, again it will be the non-final state. This is what the overall DFA diagram for this regular expression. Now you may ask, no, sir, for this regular expression, the DFA you can directly draw. Then why you are doing this procedure, sir? Because this is a small regular expression. For first time explaining the concept, I cannot take a big regular expression. I wanted to take a small regular expression. and I wanted to tell you how to do that conversion. And after that, I wanted to take the bigger size regular expression, or I can say that the language with a complex string. If I directly take a initial step itself, you will get the confusion. That is the reason I will take a small thing, and this is the DFA which I want. But I want to do this with the procedure. How to do that? So you can take this epsilon NFA, and it consists of the states of Q0, Q1, Q2, Q3, Q4, and Q5. Here the Q5 is the final state, Q0 is the starting state. Now I can come to this procedure. What I supposed to do? Convert this into DFA. Okay, by using what? Subset construction algorithm. Along with that, I have to add one more feature is called as a E closure. Okay, so what is that E closure? E closure is nothing but epsilon closure. What is that meaning? Whenever if I wanted to compute this E closure, the E closure is the function. So that function will be applied to each and every state. By the way, as per my diagram, I have a 6 state. So the state name is called as Q0, Q1, Q2, Q3, Q4, Q5. So here I have to use the function symbol. The function of what is the name of the function? E closure. If I apply the E closure function to this Q0 state, what result I will get? Generally, what is that E closure? E closure is nothing but whenever if you are in one state and without reading any input, what are all the states generally you can able to reach? Okay, so that is what we will call as E closure. By the way, without reading anything, you will be there in your own state itself. It means E closure of every state, the state itself is the first result. Next, from a state, without reading any input, what are all the state you can able to reach? That is what the overall idea of this E closure function, or I can say that the result of the E closure function. Okay, so now what is that actually the meaning is without reading any input means what? The lambda transition, explicit representation of lambda transition. That is what the understanding of this E closure. Okay, so first you can compute for a Q0. If I'm there in the state Q0, okay, without reading anything, I can go to Q0 itself. So Q0 would be the first result for me. Next, by reading lambda, I can reach Q1. So without reading anything, I can reach Q1 also. And without reading anything, I can reach Q3 also. From Q1, if there is any lambda, that also should be counted. From Q3, if there is any lambda, that also should be counted. But from Q1 and Q3, I don't have any lambda transition to move further. By the way, the E closure of Q0 is Q0, Q1, Q3 alone. Q0, Q1, Q3 alone. By the way, first you have to compute the E closure of all the states. So what are all the states are there? That state is called as a Q0, Q1, Q2, Q3, Q4, Q5. So I suppose to first compute the E closure of all the states. So the same way I will go to Q1. From a Q1, I don't have any explicit transition of lambda, but whenever if I'm computing the E closure of Q1, the Q1 itself is the result. So I added Q1 here. See, again, I'll tell you why I have practiced this example in the paper and take a screenshot. It means with a wireless mouse and this PDF screen, I cannot write like this. Please do understand that is the reason I took time to write it in the paper and take a snapshot and put it to you for explanation. If it is the class, it is the very happiest thing to discuss the subject or learn the subject like automata and formal languages. But in online, so I'm cannot write as like in the blackboard. Okay, so okay, now I can come to that. CLOSURE. Okay, so in the continuous writing I like that, but the spelling is CLOSURE, closure. What about Q2? From a Q2, the state itself is a result, and from a Q2 reading lambda, I can reach Q5 also. So the Q5 is also a result. What about E closure of Q3? There is no transition, so Q3 alone as the result. Q4, from a Q4, I will go to Q4 itself, that is one result. And reading lambda, I will reach Q5 also, so that is another result. For a Q5, Q5 itself is the result. So these are all the intermediate result I got by computing the E closure of all the state. So why actually I need this state? Because for these states, I can consider as the name of the DFA states. Name of the DFA states. Which states? These states. Okay, so now what I wanted to do for this state, say for example, what is the name of the state? Q0, Q1, Q3 is one state in DFA. Q1 is the another state in DFA. Q2, Q5 is another state in DFA. Q3 is another state in DFA. Q4, Q5 is a state DFA. Q5 is a state in DFA. Then what is my objective? Converting the epsilon NFA to DFA, right? So initially the number of state in my DFA is what? 1, 2, 3, 4, 5, 6 state. Okay, so now whenever there is a DFA, what is the first condition? You should have a transition for all the input symbol. So what are all the input symbol you have as per the scenario? We have a two input symbol. One is A, another one is the B. So now what you supposed to do for this state? You have to identify what is the transition of AB. You have to identify the transition of AB for this state, this state, this state, this state, this state. That's all. That's all. We will get the DFA. So now how to identify the transition of A and B for this subset? What is this actually? This is what we will call the subset. Subset construction algorithm only we are going to apply, right? So what is this? Which is we will call as a subset here. This is the subset. Subset 1, subset 2, subset 3, subset 4, subset 5, subset 6. So these are all the subset. For this, I have to identify the transition of A and B. How to do that? I will come to this, the procedure. First, you will take this state, Q0, Q1, Q3. This is the state. For the state, I want to identify the transition of A. How to identify? There I have to go for the function is called as, there in the previous discussion, you learned something is called as the extended transition function. Am I right? Extended transition function using the delta cap. Okay, so that is the thing we will be used to find whether the string is belongs to the particular language or not. Okay, so that's why you can remember that there are two words we are studied with respect to a transition function. One is the transition function, another one is the extended transition function. So this is the transition function and this is the extended transition function. Okay, likewise we have extended transition function here in eClosure to compute the transition of this subset. Okay, so there I have to use the symbol is called as delta dash. So delta dash of this particular state to A where it will go. Okay, so this will go, it means which is equivalent to eClosure of, see here's a transition dash here. The formula is eClosure of transition function of this state comma A. So what is the difference between this and this? This is the delta dash of A. This is the delta of A. Why delta of A? Delta of A only I can able to get it from this diagram. Okay, so Q0 comma Q0, Q1, Q3 comma A. So delta of this whole subset comma A. What is the result I want to find? Okay, so for that result I want to find the eClosure. For that eClosure only the result of this subset to A transition. Okay, can we proceed? Yes, eClosure is outside. Okay, now I can go to inside. There are three states are there to perform A transition. What I have to do? Separate it. How to separate? Delta of, I mean transition function of Q0 comma A union transition function of Q1 comma A union transition function of Q3 comma A. Now I have to find the transition of these states separately and the result I have to perform union. For that result I want to find eClosure and that eClosure only the transition of this state to A. Okay, that's why you can see here first I drawn those states and Q0, Q1, Q3 one state, Q2, Q5, Q4, Q5, Q3, Q1, Q5, every state I draw. Then I have to find what is the transition of AB, AB, AB for all. Likewise, you have to compute the AB, AB, AB for what? All. Okay, now I can come to this. What is Q0 comma A? You can go and check here. Q0 comma A, there is no any explicit transition. Then literally what is that meaning? It is not explicitly draw, then it will definitely go to which state? Pi state only. That is what we learned from NFA, right? Okay, so here also we are currently discussing the NFA only. So Q0 comma A is not specify means implicitly it will go to pi only. So the result is pi. Next, Q1 comma A, go and check Q1 comma A, go to Q2. Okay, and here you don't want to do q1 comma a will go to q2. After reaching q2, I can also by reading lambda I will go to q5. That you no need to do. That you no need to do, especially for computing the transitions in the e closure. That is very important unique thing. Generally the normal transition you will write, but here it is not needed. Okay, so why I can say it is not needed means definitely for this result what you are doing e closure, no, that time automatically that q5 will be added. Okay, you just write and see how it will differ. Okay, so if you are directly writing means there is no separate e closure computation. Okay, so you just write and you get to know how we will normally write in q2 q5 how it will be getting in the e closure. That logic you can get next moment you will get. Next, Q3 QA. Q3 to Q3, there is no A transition, right? So definitely it will go to pi only explicitly. So pi. So now if you want to union this pi union with the Q2, Q2 only. Q2 union with the pi, Q2 only. So now you have to compute the E closure of Q2. Okay, so now if you go for a E closure of Q2, that E closure of Q2 consists of Q2 and with the lambda transition I will go to Q5 also. So now what is this? This is the state where you can able to draw the transition between Q0, Q1, Q3 to A. I already told you what are all the result you will get. That is the result of DFA states. Okay, so now from the state, the transition of A, where it will go, that is what you have find as of now. The transition of A will go to Q2, Q5. That is what we find here, right? A Q2, Q5. Q2, Q5. Okay, and if you don't want to perform this procedure, what is the other procedure you can have? Say for example, Q0 to A, Q1 to A, Q3 to A. The previous knowledge we have, right? It is a whenever you are counting this transition of A, after reading a transition, is there any chance of lambda? That also you can count it. In that way also you can arrive the same result. But this is the procedure available in the function is called as E closure. There is a separate function is called as E closure. Okay, so now I have did only one transition. Now I have to do for B for this, the same AB for this, AB for this, AB for this, AB for this, AB for this. Then only I will get the final result. Okay, so now I'll come for B. What is B? What is the formula? E closure of transition function of Q0, Q1, Q3, comma B. It will be expanded by what? Transition function of Q0, comma B, transition function of Q1, comma B, transition function of Q3, comma B, all are union. And for the result, I have to find the E closure. So what is the result of Q0, comma B? From Q0, there is no B. From Q1, there is no B. From Q3, we have a B for Q4. So the two things are lambda, sorry, pi, and only that Q2, Q3, we have a result. Okay. And please, I will tell you the way you have to give numbering to the state should be a common. Then only in the examination I can able to evaluate you properly. The order is you have to give a state name 1 and go up till this level, come down, complete, and go to the next level. Okay, otherwise I will get the mismatch result in the state. Okay, so what is the result I have? E closure of Q4. What is the E closure of Q4? Q4 and Q5. So that I can able to include. So every time again I have to go and check here. No, that's why I have compute the E closure of everything at the beginning of the process itself. So what you can simply do, E closure of Q2, you can go here and find Q2, Q5, write it here directly. E closure of Q4, go to here and find it here, write it directly. No need to do it again because I already did and I have a result in my hand. Why I have to keep on doing for every time? Okay. So from this, what is the conclusion? The Q0, Q1, Q3 is one of the state in the DFA. The transition of A will go to Q2, Q5. The transition of B will go to Q4, Q5. So I already told you for all the result, you draw the state. For A will go here and B will go here. Okay, so that alone I have find it as of now. Then what is the other thing? I will do the same for the remaining also. So what is the remaining? I will take Q1. Transition of A and B. So what is the transition of A and B? E closure of transition function of Q1 comma B. From Q1, I don't have any B transition. So literally it is null. What is the E closure of E closure of pi? E closure of pi is pi only. It means what? Q1 comma B will go to state is called as a pi, right? Okay. What is a Q1 comma A? Again, you can go and check Q1 comma A. Q1 comma A will go to Q2. So uh, Q1 comma A will go to Q2. So what is the E closure of Q2? Q2 Q5, where I can able to get here Q2 Q5. So now Q1 comma A will go to Q2 Q5 state. Okay, so this is a second set. So what is the third state? Q2 Q5. Take Q2 Q2 Q5 delta dash of Q2 Q5 of A, which is equivalent to E closure of transition function of Q2 comma A, transition function of Q2 comma Q5 comma A. What is Q2 comma A, Q5 comma A? From Q2 there is no A, Q5 there is no A. Both are pi only. So the E closure of pi is pi only. It means what? Q2 Q5 A will go to pi state. Okay, now we can come to B. Delta dash of Q2 Q5 of B, which is equal to E closure of transition function of Q2 Q5 comma B. So Q2 comma B, Q5 comma B. What is a Q2 comma B? Pi. What is a Q5 comma B? Pi. So E closure of pi is also pi. Where I can able to confirm? Go and check. Q2 B5 pi and Q5 also pi. Okay, so now I can come to the fourth one, Q3. See here, transition function of, delta dash of Q3 comma A, delta dash of Q3 comma B. So the Q3 comma A is E closure of transition function of Q3 comma A. What is Q3 comma A? From Q3 there is no A, so again pi. So E closure of pi, pi only. Q3 comma B, Q3 comma B will go to Q4. You can check here. Q3 comma B will go to Q4. Then what is the E closure of Q4? Here you can check Q4 Q5. So E closure of Q4 is Q4 Q5. So now I have completed till this state. Now I can take this state Q4 Q5. Q4 Q5. I want to do the both A and both B. So what I wanted to do with that, again same E closure of transition function of Q4 comma A, E closure of transition function of Q5 comma A. Q4 Q5 comma from from Q5 there is no A transition, so both will go to pi state only. So from a pi state, E closure of pi is pi. So next I can come to Q4 Q5 B. So E closure of transition function of Q4 comma B, Q5 comma B. Q4 comma B is also pi, Q5 B comma also pi. So E closure of pi is pi only. So I have completed this state. I have completed this state. Then I can come to the last state, Q5 comma AB. Okay, so transition dash of Q5 comma B, Q5 comma A. So that is Q E closure of Q5 comma A, Q5 comma B. Both from Q5 there is no transition, no, it will go to pi state only. Okay, so now as per this state, I have completed the transition of all the state for A and B, because that is the nature of DFA, right? So now I will draw all the state 1, state 2, state 3, state 4, state 5, state 6, and everything will go to pi state also, right? That also you have to include. Okay, so we have a 7 state as of now. Now, next step. What is a starting state? Whenever you have find the E closure of the starting state, where it will go, that resultant state I can call as, or where do we have a Q naught, the state I can call as a starting state. Okay, so now I will go to that state and say that that is the starting state. And what about the final state? What is the final state here? Q5. Wherever in the subset we have a Q5, all the states are final state. So here we have one final state, two final state, three final state, because these three subset will have a Q5. So this will have a Q5. So this is one final state, double circle. This is having Q5. So this is a final state, so two circle. This is Q5, two circle. Okay. So next, starting and final state is over. You just read this transition. That's all. From the state to A, where it will go Q2 Q5, and B will go where Q4 Q5. Just come to this and draw. A will go to Q2 Q5, B will go to Q4 Q5. Next state is what? Q2 Q5. So now go to Q2 Q5, where the Q2 Q5 will go. Sorry, okay, Q1 you can see. Q1 comma A will go to Q2 Q5, B will go to pi. So Q1, A will go to Q2 Q5, B will go to pi. Next, Q2 Q5, A will go to pi, B will go to pi. So from the state, both A and B will go to pi state only. Okay, so next Q3, A will go to pi, B will go to Q4, Q5. So from Q3, A will go to pi, B will go to Q4, Q5. Okay, next come to this Q4, Q5. Q4, Q5, A and B both will go to pi state only. From Q4, Q5, both A and B will go to pi state only. Okay, from Q5, both A and B will go to pi state only. Okay, so now for your visualization, for better understanding, I draw the diagram. I mean, here, if you feel that it is in the bottom, it is clumsy, then I can redraw the same diagram in the detailed manner. So what is this? This is what my DFA, deterministic finite automata. For what? For the regular expression of A plus B. Now you may ask the question, sir, you draw initially before you did this process, this is the DFA, consists of only 3 states. But you can see here there are 7 states are there. Then you can say that this is also DFA. That's why I told you. Next step in the DFA, we have something is called as minimization of DFA. Okay, so there you have to apply the minimization of DFA from the result to get the result as like this. Get the result as like this. So for that we have a 2 procedure. Okay, so the first procedure is called as state equivalence method. The second procedure is table filling method. Okay, so based on these 2 methods, either you can follow any one of the method to convert a given DFA into minimized DFA. That minimized DFA is only the result of converting regular expression to DFA. So please remember that whenever there is a question about a regular expression to DFA, you have to do 3 steps. Step number 1, convert the regular expression to epsilon NFA. Step 2, convert the epsilon NFA to DFA. Third step, convert the DFA to minimized DFA, MDFA. So what is algorithm for regular expression to epsilon NFA? Thomson construction algorithm. What is algorithm for epsilon NFA to DFA? Subset construction algorithm with E-closure function. What is the DFA to minimize to DFA? Either the state equivalent method or table filling method. So everything we have a procedure. There is a procedure, there is algorithm. Accordingly, we have to perform. Okay. So before I discuss one more example, okay. Before I discuss the one more example, I wanted to explain here itself the minimization also, because the minimization we have a separate discussion, but here I will do it for better understanding, because I already show what would be the expected result here. But how we will get this, I don't want to take as a separate component, because the continuation of this result only that minimization. So now before we can do the minimization of DFA, first we have to identify what are all the non-reachable state. Non-reachable state we have to first identify. Then only you have to apply either the state equivalence or the table filling method. So what is a non-reachable state? First you have to identify the non-reachable state from the result of DFA. And whenever there is a non-reachable state, you just simply remove it. That is the meaning of, that is the purpose of finding the non-reachable state. What is a non-reachable state? From the starting state, what are all the states in the DFA we cannot be able to reach? Those states are called as a non-reachable state. It means this is a starting state. From the state reading A, I can go here, fine. From the state reading B, I can go here, fine. Now, you can consider here. From a starting state reading A, I will go here, but by reading what, I can reach Q1. There is no any in degree transition for Q1, right? See here also, the Q1 will have a 2 transition, both A for here, B for here, but both are not reachable. How we can able to reach Q1? Via this also there is no path, via this also no path. It means the Q1 is the non-reachable state. So there is no use of being that Q1 in this picture. Okay, so that's why you can remove the state from the DFA. Okay, now you can come to this Q5. Both the transition of A and B will go to pi, fine. But what about the way to reach Q5 from a starting state? We don't have any in-degree transition to Q5. So this Q5 also not reachable. So you can remove it. Okay, next. Come to this state. And this can be reachable, right? From B, you can come here, and reading AB, you can come here. So this could be reachable. Now you can think about this state. Q3, how to reach from this no transition. Here also no transition. Both are out degree transition. So the Q3 also not reachable. Okay. So now you have only 4 state in your hand. So this is the state 1, state 2, state 3, state 4. So now from the result, you can apply the state equivalence method. Okay, so what is the result you have? Q0, Q1, Q3, one result. Q4, Q5, another result. Pi is one result. Q2, Q5 is another result. Okay. So now with this 4 state, you can redraw the diagram again for a better understanding. You can redraw the diagram here. Okay, so I can consider the whole state as Q0. I can consider the whole state as Q2. That is final state. Because this numbering is for our understanding only. No, this Q4, Q5, I can write it as a single state, that is Q3. And the pi state, I can write it as a Q4. So now Q0 to A will go to where? This state, Q2. Q0 to B will reach here. So the transition of AB is over. The transition of Q to AB will go to where? Pi state. And the transition of this AB will go to where? This is also pi state. So from the diagram, I draw the thing. Okay, so by default, the pi state, or I can call it as a Q4, the AB will go to there itself because this is a non-reachable state, right? So this is the final result you have, not a final result. After removing the non-reachable state, this is the result of DFA you have. So from the result only, you have to apply the minimization of DFA. So for small example, I will tell you how the state equivalence method will apply over this. Okay. So what is the state equivalence method? So you first make it 2 set of states. So there are non-final state into one set, final state into one set. So here the Q0, Q4 are non-final state. Q0, Q4 are non-final state. And Q2, Q3 are final state. Okay, so now what you supposed to do, is there any chance the states available in the final or state available in the non-final we have a same behavior, then we can able to combine these two. That is what the minimization will do. Right. So minimization purpose is what? Reduce the number of state. So how to do that? If there is any similar nature, then we have to reduce. What is similar nature? The transition of Q0 AB and transition of Q4 AB will follow the same pattern. Then we will merge these two. The same way the Q2, Q3 will follow the same pattern, we will merge this. So what is actually the pattern? The pattern may be Q0, A will go to one state. Say for example, the non-final state. In this state, the Q4 AB also will go to the same state. Then I can merge it. This is what the procedure. Now we can see the example I will tell you. For Q0, A will go to the other set. It means a final state set. Q2 is the final state set, right? The Q0, B also will go to the final state set. If Q4 also will have a same pattern, then I can merge it. But you can see the Q4 AB will go to Q4 itself. It means a non-final set. So the Q0, Q4 don't have a common pattern. So I cannot have a chance to merge these two. So the Q0 is a separate component for me and Q4 is the separate component for me. I cannot merge these two. Okay, so the starting state of Q0 is not changed, but I cannot merge this. come to Q2, Q3. Q2 of AB will go to Q4, that is non-final set. The Q3 of AB will also go to non-final set. It means what? Both will have a same pattern. So then there is a chance I can able to merge these two. I can able to merge these two and put it only one final state. Now you can explore the transition from here to here. Q0 comma A will go to where? Q2. Q0 comma B will go to where? Q3, which is available where? Here itself. So A comma B. Okay. And Q0 comma AB will go to where? Q4. Okay. Q3 comma AB will also go to where? Q3 comma AB also will go to where? Q4 itself. Then Q4 of AB will go to where? Q4 itself. Now, is there any other chance to minimize this further? No, this is a final minimization. Then this is what I can say that the result of minimized DFA. M DFA. Now you can just observe this diagram and go to this. This is only I draw there, no? From a state, AB will go to one final state. From a state, the AB will go to a non-final state. From a state, we have AB from the same state. So what is it meaning? With before I can come to this conclusion, I draw this result by looking at that regular expression itself. Am I right? By looking the regular expression itself, what is the expected minimized DFA I want? I did. But the same thing by applying the procedure I did, and I can prove the same result. So now you can see the actual thing what we did for this conversion, epsilon NFA to DFA conversion with the minimization. So I did the minimization also. Okay, so this is the minimization. So this is the procedure to apply the minimization. Okay, so there is other method for minimization, that is a table filling method that I will explain in unit number 2, because we have a dedicated chapter for a discussion of this alone. That time I will discuss. Okay, so with that I will stop the discussion of today's class. See